three equations. First, momentum conservation in the x direction. We have, remember that the masses are equal, so I'm going to call all masses m. So in the x direction, initially you have just momentum of ball B, so mvb, and that's equal to final x momentum, which is m times the va prime x, and this is momentum of velocity of ball A in the x direction after collision. So momentum of ball or velocity of ball B is entirely in the or velocity of ball B after collision is entirely in the y direction, as we see from the figure. So that doesn't come in here. The masses cancel, and we have that velocity of B initially is equal to the x velocity of A after the collision. Okay. Second equation we're using is P is as a momentum. So let's call this equation 1. Second equation we're using is momentum conservation in the y direction. So in the y direction, you have initially you just have velocity of A. So momentum times velocity of A, VA is equal to momentum times velocity of A in the y direction afterwards, mVA y prime, plus mVB prime, and remember VB prime is equal to VB y prime because there's no x component to that. Okay, and so the masses again cancel here, and we are left with VA is equal to VA prime, VA y prime plus VB prime, and that is equation 2. And the third equation we're going to use is the conservation of kinetic energy. So initial kinetic energy will be equal to final kinetic energy. Initially, you have 1/2 mVA squared plus 1/2 mVB squared. Finally, you have 1/2 mVA prime squared plus 1/2 mVB prime squared, because energy is only about magnitude, not direction. Remember that. So the half m factors cancel from every term, and going to the next page, we're gonna get VA prime plus VA squared plus VB squared. Is equal to VA prime squared plus VB prime squared, and that is equation 3. Now what we're going to do is plug in 1 and 2 into equation 3, and what we get is, so VA from equation 2 is VA y prime plus VB prime. So VA squared becomes VA y prime plus VB prime quantity squared, plus VB squared is, so VB from equation 1 is just VAX prime. So VAX prime squared, that's equal to VA prime squared plus VB prime squared. Let's expand out these terms. So this is VA y prime squared plus 2 times VA y prime times VB prime plus VB prime squared plus VA, this will be VA VAX prime squared is equal to VA prime squared plus VB prime squared. And so we see a VB prime squared on both sides. That cancels. More, you have, notice on the left-hand side, you have 2 VA y prime VB prime plus VA prime, because VA prime squared is just VB, is VA y prime squared plus VA x prime squared, right? It's the magnitude of the two. It's the square of the magnitude of the two of the x and y components of A prime, which gives VA prime. So VA prime y squared plus VA prime x squared is VA prime squared, and that is equal to VA prime squared. And so those cancel. And we're left with the unsettling realization that the final answer here is 2 VAY prime times VB prime is 0. Okay, so what does that mean? That means that either VB prime equals 0 or VAY prime, or the y component of VA prime, is 0. And this cannot be true because we already know that VB prime is non-zero from the figure. So this implies that VAY prime is 0. So VA prime has no y component. Okay, so this just means that VA prime is equal to VA x prime. It's only in the x direction. All right, therefore VA VA prime in x direction is one of the answers, and the other answer is what are VA prime and VB prime. So VA prime is just VA x prime, which is from equation 1 VB, and VB, as we know, is 3.7 meters per second. So there's that. And VB prime is just from equation 2, it's VA prime minus VAY prime, but VAY prime is nothing. So it's just VA, it's just VA, excuse me, not VA prime. So VB prime is just VA, which was 2 meters per second. And that's it.